Hello, everyone, and welcome to another Beneath the Surface lecture with today, Mark Jackson from National Weather Service, located up in Oxnard. That's where Mark is. I'm going to introduce him real quick. Mark Jackson is the Mark is the meteorologist in charge of NOAA's Los Angeles Oxnard National Weather Service. Mark has been the meteorologist in charge in Oxnard since 2005. Over the span of his just over 25-year career with the National Weather Service, Mark has served on numerous scientific and programmatic teams, including the team to create the 2009 National Weather Service Strategic Plan to build a weather-ready nation. And most recently with the agency's Evolve Program Management Office, tasked to build enhanced impact-based decision support services. Mark has a BS in meteorology from the University of Nebraska-Lincoln and an MS in meteorology from the University of Oklahoma. Mark and I have gone back a little ways, working on a bunch of projects with where I used to work at the Aquarium of the Pacific. And over these years, it's been really a great pleasure to, Mark, to get to know you and to benefit from all of the wonderful information that you've been able to share with various audiences and bringing kind of this, bringing weather and weather impacts and climate impacts to the broader public, which I think is really important. And I'm excited to learn a little bit more about what you're going to share tonight. So without further ado, I'm going to pass it over to you and we'll get started.
All right. Thank you, Dave. I'll go ahead and take the screen, I guess, when you can hand it over to me.
Yeah.
Let's see.
Go ahead.
Okay. All right. Let me try this again.
I swear it all worked 30 seconds ago. All right, we're back.
Oh, there we go. Yeah. All right. Thanks. Thank you, Dave. And it's good seeing you again. Yeah, Dave and I go quite a ways back, Aquarium of the Pacific in Long Beach, and we've been doing quite a bit of work with the aquarium and outreach and various documents and brochures that we've put together. Jerry Schubel, who was the former executive director of the aquarium, near and dear to his heart was climate change. And in fact, my very first public climate change talk as a meteorologist in charge was at the Aquarium of the Pacific. It was during we did NOAA Day. Actually, they still do NOAA Day at the aquarium, and this was one particular NOAA Day that they had some teachers that listened to me talk about climate change. It was pretty interesting. But where we have come from a perspective of the National Weather Service and being able to really talk about climate change is really kind of an indicator of how far the science has come and how many allowances we have really to be able to now talk about climate change. So thank you, Dave, for inviting me to speak to the group. I can't see you all. I would say it's good to see you, but I can't see you. All I can see is the screen. And what Dave wanted me to talk about was really, from an ocean standpoint, of course, the three main things that we're talking about with the blob. And you can see a picture of the blob right there on this screen background. Also El Nino, La Niña, and then our changing climate. All of these have impacts on marine mammal life. Now, just as a disclaimer to start, I am a meteorologist by education and by profession. This goes a little, this crosses into the water side of NOAA a little bit. I joke with other NOAA people that most encounters I've had with a NOAA administrator have been on the water side, some sort of water event. But I did learn some things, the power of Google, and hopefully it might create at least a few questions and get you thinking a little bit. So Dave said a little bit about myself. I thought I would go a little bit more into that to kind of give you a perspective of really how I grew up landlocked, right? I was born and raised in Omaha in the Midwest. As he said, bachelor's in meteorology from the University of Nebraska and then University of Oklahoma. I'm a Cornhusker at heart, so ignore the University of Oklahoma part. I then went on to work at NOAA's Forecast Systems Laboratory in Boulder, Colorado. And And then following that, entered into the National Weather Service in 1995. And I've been kind of doing the loop around here. Started out as a science and operations officer in Brownsville, Texas. The SIU, as they call them, are responsible for technology transfer and also training. And then I went from there on to Honolulu, Hawaii as a regional scientist. And it was that was the view. And that picture you see in the upper right of the slide was actually a view from my office. I took that one morning, and that's the picture that shows up on their internet homepage. And so anyway, it really, I've learned to love the ocean, okay, between Brownsville and Honolulu. I went back into the landlocked in Salt Lake City again as a SIU. And now I've been in Oxnard here as a meteorologist in charge. We have an office of about 26 people or so, 24/7 with, we provide forecast and warning support for Los Angeles County all the way up to San Luis Obispo County. And we're fortunate enough to have quite a few other NOAA agencies within our area, not only Southwest Fisheries down in Long Beach, but also the Channel Islands National Marine Sanctuary up here in Santa Barbara, and then also in Ventura. So again, we've had this interaction with the water side of NOAA, and I consider ourselves very lucky to be able to do that. So here's some important points to get across as we head into this. It's very important to understand this first bullet here as far as what climate is. And this was a quote, I forget where I heard this, but storms make weather and weather makes climate. So, yeah, we're able to look outside right now and observe what the weather is. It's here in Oxnard, it's sunny. I'm looking down at 64 degrees. Okay. That's our weather. Storms make up part of that weather. But when you look at climate, that's a much longer trend and period of temperatures, observations, weather occurrences, but it has to occur over a much longer period of time. And even though it's becoming more and more obvious that climate change is impacting our instant weather in terms of our storms, but only in the number of storms and extreme weather that we're experiencing. So another thing here, through all of the research that's been done on climate change, there's no question here in terms of the unequivocal warming of the climate system. And that's throughout everything. That's in our oceans, that's over the land, and especially over our oceans. El Nino Southern Oscillation, that's ENSO. That's made up of El Nino, which is the warm episode, and La Niña, which is the cold episode. And both of them can have impacts on our weather out here in California, but it requires not only the warming of the ocean, but also the coupling of the atmosphere. And I have some slides that go over that as well. And it can have dramatic impacts in seasonal conditions over the West Coast and the West. Growing up in the Midwest, for instance, my image of El Nino is our houses falling into the ocean in California. And so, of course, very, very big storms that can impact California. And with El Nino, as at the same time, La Nina, as I'll show here in a minute, can bring very dry conditions. The blob, and the blob is kind of the street term, and it's called it's a marine heat wave. And really, it's kind of a chicken and egg thing. But it's really believed to be caused by this stagnant high pressure, and it kind of feeds off of itself. So when you get this large high pressure ridge over the northern Pacific, and then that just encourages more warming of this blob of ocean in the North Pacific, and that also has impacts on the upwelling along the West Coast. And all in all, all of these can have temporary or even permanent impacts on marine life, and that's one of the big takeaways. Reference material, I'm a meteorologist by education and profession. I'm not a climatologist. So one of our primary responsibilities in the National Weather Service, though, is to communicate the impacts of climate change, observations of the climate, of course. And we are definitely an outlet to the public to be able to do that. So as I'm doing right now, one of the really most powerful sources for climate change information is from the Ipcc, which is the Intergovernmental Panel on Climate Change. And they're now up to the 6th assessment report, but this is the 5th assessment here that was published in 2014. And it's important to know that they don't conduct their own research. They instead are gathering research from all over the world. And when they break it down into working groups, and when you look at those numbers there in terms of the lead authors, the countries represented, when you consider, if you go to a doctor and the doctor gives you a certain diagnosis, a lot of times, especially if it's kind of in question, you want to get more opinions. So you get second opinion, third opinion. Well, when you look at these, how many lead authors in there? It's when you read then something like what I had in the first bullet, unequivocal warming, that the consensus of information in here is very powerful. And so I invite you, if you haven't been there, to check out the Ipcc website, ton of information on there. Bringing it down more to the local area, there's the 4th National Climate Assessment, which is from 2018. You can see the website there. They are conducted under the auspices of the Global Change Research Act, 1990. And you've got those 2 reports are very informative down into the California scale. And in fact, there's information in this California's 4th Climate Change Assessment. Actually, Jerry Schubel, who I mentioned earlier, who was the director of the aquarium, has a section in this California Climate Change Assessment. And then moving on, this is hot off the press here, relatively speaking. This is the 6th assessment of the Intergovernmental Panel on Climate Change. Working Group 1 produced their report in August of 2021, and then Working Group 2 here just recently in February of this year. There's other reports on their way. 3 should be out here pretty soon here. And then also the synthesis report in September of 22. So here's some of the headline statements, and there's gonna be a lot of words here. I'm just gonna go through here, but this is from the 6th assessment, Working Group 1, again, the physical science basis. And very powerful statements, and these are straight from the 6th assessment. But when you look at the changes of the climate system as a whole, they are unprecedented over many centuries to many thousands of years. And then human-based climate change, already affecting many weather and climate extremes in every region across the globe. And that sub-bulletin there, in terms of the extreme conditions, heat waves, heavy precipitation, droughts, tropical cyclones, and then the human influence, it's strengthened since the 5th assessment. So when they get these additional assessments, many times you'll see that where they say the evidence is even stronger than the previous assessment, and that's a very powerful statement. But when you look at extreme events such as heat waves, heavy precipitation, droughts, we've always had heat waves, we've always had heavy rain events, extreme flooding, extreme droughts. But when you look at it, we're seeing an increase in the number of these events. And the best analogy is really kind of baseball and steroids. So or performance enhancing drugs. Any baseball player out there can hit a home run if the bat hits the ball just right, they'll hit it out. But when you start seeing a player who has rarely hit any home runs, all of a sudden now start to hit more and more and more home runs, you have to start to wonder something's going on here. So when you think of extreme events and climate change, think of numbers and frequency. So, and also global surface temperature continued to rise until at least the mid-century under all emissions scenarios considered. So when they look at climate projections, they consider different emission scenarios, and I have a slide that goes over that. And all the way from 0 emissions up to the worst case scenario emission. But again, 1.5 to 2 degrees exceeded in the 21st century. And one other thing to make a point on, you might think, well, 1.5 degrees Celsius change, what's the big deal? Well, what happens is that bell curve now shifts over to where the area that's in the middle of that bell curve has shifted over, and you get kind of tails that come down on either side of the bell curve. Well, as that one tail out towards the hot end, if you're looking this way, hot this way, now you've increased the number of the probability of heat waves, essentially. So 1.5 to 2 degrees can have very dramatic impacts. And then changes to the climate system become larger in direct relation to increased global warming. So as we warm, in the frequency and intensity of hot extremes, marine heat waves, as I just said, the probability increases. Many changes due to past and future greenhouse gas emissions are irreversible for centuries to millennia, especially changes in the ocean, ice sheets, and global sea level. All right, so when you talk about zero emissions, when they just stop everything, we've really passed the tipping point, and there are still impacts that continue even if you were to shut off all emissions. And then this last bullet is kind of interesting because, you know, it's kind of interesting because there's these weather movies out there like Twister and those. One of the most interesting movies I think is Day After Tomorrow. Say what you want about it, but it's not a bad movie. I usually stop by it if I'm channel surfing. I'll stop and I'll watch it. But when you look at some of these like abrupt ocean circulation changes, compound extreme events, that they were assessed in a very likely range, they can't be ruled out, and they're becoming part of this risk assessment. This is language that really wasn't, hasn't been included in previous working group assessments. So then as you move on to working group 2, and this is where you talk about impacts, adaptation, and vulnerability. And again, there are widespread adverse impacts related to the frequent intense extreme events, from losses, damages to nature and people, beyond natural climate variability. All right, and that underlines sentence there is pretty important because, again, this hasn't shown up in recent reports, and it does show that maybe there are some things that are making a difference, but the development and adaptation efforts have reduced some vulnerability, and that's good. 3.3 to 3.6 billion people live in the context that are highly vulnerable to climate change, and high confidence, as you see, that those are always with every one of these reports. All right, a high proportion of species is vulnerable to climate change. It impacts everybody practically. And then here, the statement on global warming reaching 1.5 would cause unavoidable increase in multiple climate hazards, present multiple risks to ecosystems and humans, and very high confidence with this statement. Climate change impacts risks are becoming increasingly complex and more difficult to manage. That's another very interesting statement, concerning statement. But again, things are kind of piling on right now, and it's very difficult to really kind of adapt to some of these things. And then if it exceeds 1.5 degrees Celsius in the coming decades or later, then many human natural systems will face additional severe risk compared to remaining below 1.5 degrees C. And then finally, there has been progress in adaptation. Planning and implementation has been observed across all sectors and regions, generating multiple benefits. And that's why, again, there at least are some encouraging signs, and adaptation is a very important part of that. So let's look at some data. And again, this is coming straight from, this is from the Ipcc AR5. And you can see on this graphic, you look at, this is combined land and ocean surface temperature anomaly. If you can see my mouse there, this is from 1850 to 2012. And this is compared to a baseline. So when you look at climate, you always want to compare to a baseline period. So this is compared to a baseline of 1986 to 2005, okay? And you can see that this really, especially since the, kind of like the late 1920s, late 1920s, 30s, 40s, and really this jump up. And then I like actually looking at the decadal averages as well. It really helps to break it down. And then this bottom graph shows the observed change from over 1901 to 2012. And there are some relatively cooler spots than others, but for the most part, you have warming. And then when you look at the sea ice extent, and this is from the Arctic, July, August, September. This would be kind of that ice that never goes away, right? And so you have that extent going down, and then the sea level change going up. And I'll say more about the sea level change here a little bit later. So 2021, when we look at globally, where we sit in terms of anomalies, temperature anomalies, 2021 was actually only the 6th warmest on record. A lot of that was because of the La Nina conditions. that existed within 2021. That's that blue area that you see coming off of the western side of South America. And that does have a big impact globally, believe it or not. You can see though that this trend here, when you look at the temperature anomaly, again, this is compared to a baseline value in this case, and this looks at really the rapid increase that we're seeing, especially over the last 50, 60 years or so. And then the human factor. All right, so you look at CO2 measurements, and you can go way back with CO2 measurements, of course. You look at ice cores and everything else. It's really a very fascinating science. But going back 800,000 years with a combination of ice cores and observations, it's just incredible. And you can see that there are natural variations in CO2 levels, all right? Not only on a seasonal level, when between the winter and the summer, based on absorption of CO2 within the vegetation and emission of CO2 within the vegetation, things like that. But then you look at what's happening here in this rapid rise that has occurred over on the left of that graph, right on the left of that graph, and then really kind of as it matches up on top of what we see with some of the temperature trends as well. So this is one way to visualize this. So down here, just imagine this is now a trend, atmospheric CO2 that goes, this just goes back, it might be kind of hard to see, but back to 1950, you can see those little squiggly lines and in between the main rise, and those little squiggly lines are seasonal natural variations in CO2. But then when you go on top of that, so this is what it's called representative concentration pathway, so RCPs. And there are 4 different RCPs that are overlaid on here. So if you look at that slope in observed CO2, and if you just extrapolate that on up until the year 2100, you can maybe get an idea of what kind of slope we're on. All right, and you might even say that between those RCPs, we might be on a trend of if we continue at this pace of that RCP 6.0. All right, and then all the way up. Worst case scenario when they run these climate models is at 8.5 RCP 8.5, and that's actually it's in the blue line up there. So, or the purple line. So, and then even going down below that 2.6, you still get kind of an increase. So let's look at the ocean. So again, this is a 3-month heat energy in the top half mile of the ocean. And this compares to that 1955 to 2006 average. And you can see this trend in ocean heat content, those red bars that have really picked up some steam here going back through the 2000s. And then some of the projections of ocean warming. And here are these RCPs on here. So you have in that blue, that RCP 4.5, we're kind of on a trend somewhere between that 4.5 and 8.5. And then that sea surface temperature and projected by 2100, again, that increase that you would see. And again, going back to, well, you might say, well, 2 degree Celsius temperature change. Well, now that increases your probability of these marine heat waves and things like that. Sea level rise, and this is kind of an interesting thing too, because there might be this kind of misperception out there of what causes sea level rise. And just as a fun science experiment, go put ice in a glass of water and watch the ice melt, and the water will not overflow. So it's not the Arctic that has impact on sea level rise. It's the glaciers. It's landlocked ice. It's expansion, thermal expansion of the oceans as they warm up. But again, it's the glaciers. It's we look at any sort of melting off of Greenland, for instance, or Antarctica. It's ice that normally is locked on land that then becomes that then moves over to the water. And you can look at that global sea level. And really when you look, especially at the satellite data, and I'll show you a real fascinating graphic here in a minute of very detailed satellite data based sea level rise. And again, that's, you know, as a matter of fact, we had not too long ago a launch out in Vandenberg that launched the Jason satellite, which is part of what's measuring the sea level elevations. This is that graphic I was talking about, and it's really interesting because this is the regional sea level change between 1992 and 2019. So the dark red colors are the higher sea level change between that time period. And this is based on multiple satellite altimeters. The blue regions are where you're seeing a decrease in sea level. So it's kind of hard to see that scale on the bottom, but as you get up into kind of the orangish color, that's 10 centimeters. All right. So, and what's interesting is that it's not equal across the globe. And so you look at the West Coast, and you look to see there is some rise, but not as dramatic as what you would see on the Gulf Coast on the Atlantic seaboard. All right. And then also when you look down, especially across the Southern Hemisphere in some of these areas and the kind of sea level rise they're experiencing. And then when you go out into the Pacific, and it's a very big issue when you consider sea level rise in the central Pacific and the equatorial Pacific and what's happening to the island nations out there. But anyway, very fascinating graphic to be able to see the distribution of sea level rise. Sea level rise and storm surge, and this is something that going back to, well, what's a couple of centimeters, or, you know, what's another foot or something like that. But when you put a storm surge on top of that, and so when we see what's happening in the Gulf Coast and the East Coast with these hurricanes, and, you know, some of the flooding that occurs like in New York City and things like that, and even out here when we have these strong El Nino storms and with, you know, very big waves, and a little bit of sea level rise increases that probability of overtopping, you know, the jetties and things like that. But storm surges that occur today are 8 inches higher than they would have been in 1900. And by 2100, storm surges will happen on top of an additional 8 inches to 6.6 feet of global sea level rise. And again, we're seeing an increase in the amount of nuisance, you know, tidal flooding. And then anytime we get something like this, where we get an oceanic storm, that will also increase the amount of coastal flooding. This is kind of a neat tool, and there's the website up there. I invite you to kind of go play with it. But this is, NOAA has a tool where you can visualize the sea level rise impact. So bringing it up to my own backyard up here, practically, as you go over to Channel Islands, this is what a 2-foot sea level rise would look like. And these green areas are considered low-lying areas. So they are hydrologically unconnected areas that may also be flooded. So what you're looking at is a much higher occurrence of flooding, you know, based on, you know, exceptionally high tides, for instance, king tides, what they refer to. Also, when you look at El Nino, when we have very warm water, so there's that thermal expansion, and so you're increasing. There is actually an increase in the sea level rise on a seasonal basis. So that's with 2 feet, and then when you, I missed a slide in there. Okay, so let me go back. Apologize. Hold on for the ride. I thought I had 2 slides in there, but anyway, so that's 2 feet. All right. So let's change gears and talk about El Nino Southern Oscillation. What is it and why is it important to us? And hopefully when this is all said and done, you'll be an ENSO expert that you can impress your neighbors and your friends. These are 2 great examples of very strong El Ninos that occurred, one in the 97-98 El Nino, and then most recently the 2015 El Nino. And those white colors are actually sea level heights. So there's a sloshing of water around the globe, and that's actually also an indicator of that very warm water. So let's start from the basics here. When we talk about how atmospheric circulation begins, uneven heating from the sun, right? So when that heats air on the tropics, it rises, all right? So it rises, and then it has to cool and then come back down to Earth. So now you're starting this vertical circulation in these vertical cells. And then now you throw a turning globe on it. And I still have a record player. I don't know about anybody else, but I haven't used it for a while, but just do an experiment there and turn the record and hold your pen, and you're going to draw a circle as it turns. So that's a Coriolis force. And so that actually causes, as you see, the rising air at the equator and then sinking air coming back down. And then it actually causes that turning that you see there in these. So now we're talking about trade winds. And there's the start there, right there, of the trade wind blowing off of the western South America coast across the Pacific. But so if it did rotate and had a uniform surface, it would cause two convection cells, basically. And you can see that like that from north and south. But again, what actually we get is three cells. And that's called the Hadley cell, as you see there in the middle. And at times, you might get a strengthening of these trade winds, and they'll increase or decrease due to gradients in the ocean temperature. So the ocean has variations in temperature, just like we do on land, but not quite as sharp like we do on land. But again, the swaying of those gradients and those trade winds is what really results in El Nino and La Nina patterns. And so when you look at the three different scenarios, so here's a neutral circulation, and this British climatologist Gilbert Walker noted this swaying on a bigger scale. And neutral is where you don't have where the trade winds, and if you look at this picture, imagine that you're looking down. This is South America over here, so you're down kind of over Antarctica, looking north across the Pacific. And so you see, normally, again, you get these trade winds blowing from east to west, and then this circulation. And what you see over on the western side of the Pacific is an increase in storms and convection, like that. El Nino happens actually when, for various reasons, these trade winds weaken. And that actually kind of allows for a sloshing back of this warm water back to the east. You can also see what's happening here to the upwelling in the thermocline. So this is a slice through the ocean. And so you've actually cut off some of that upwelling, and with this keeping the colder water further south. So if I just go back and forth here, so there is a neutral condition, and now here's an El Nino condition. And these areas of storms move over towards more of the central Pacific, and which really produces quite a moisture source for us when we have our strong El Nino storms in the jet stream. The subtropical jet stream dips down and really kind of pulls things up. So, so this again has big impacts on the upwelling that occurs. And then La Nina shifts back around, and now you have stronger than normal trade winds that really push a lot of that warm water farther west. And now you get an increase in the upwelling. So you can see where this thermocline is, and as it's coming up on the west coast of South America. So, you know, we all know the story of El Nino and how it impacts the fisheries off of South America, and for as long as that it's been going on, and it's quite a history. So how do we determine the strength of ENSO? And these areas that you see here, the most important one is this Nino, what they call Nino 3.4. And as the temperature changes over a 3-month period in that Nino 3.4, that determines whether we're in an El Nino or a La Nina. And you look at 5 consecutive overlapping 3-month periods to really call yourself in an El Nino. And I'll show a graph here that really helps you decide. So neutral is in that where that ONI is between 0.5 and minus 0.5, and then above it is El Nino, and below it is La Nina. So typical ENSO timing, and most El Nino events begin in the spring, can last through the following spring or summer. This graph shows quite a few of these Nino 3.4 values, and you can see here they are. They kind of peak up, and they're warmest here in November. Then they start to kind of climb down again. But you can see some of these values in 2015 and 1982, 97, some of the strongest El Ninos that we've had, really. 2015, really kind of the strongest. and you can see where those kind of peak and as they fall right down. So it's this constant balancing of the atmosphere and ocean system. So, you know, you won't have back-to-back strong El Nino years, because the atmosphere wants perfect balance, and the ocean atmosphere system wants perfect balance. And when it goes too far, it wants to come back. And then what happens? It overshoots. And so that's why you get this up and down of El Nino, La Nina, neutral, and things like that. And here's some of the typical jet stream patterns across North America. So La Nina, where the jet stream goes way up into the Gulf of Alaska, comes back down. You get primarily wet conditions in the Pacific Northwest. We're typically drier along the southern tier states. And then it switches then with the El Nino, where the jet stream moves further south, and you have very warm conditions up north, very wet across like Southwest California, all the way across the southern tier states. And so in climate change, would we expect more El Nino or La Nina events with a warmer climate? And really what the takeaway really is that we may not see more, but we would likely see stronger. And you have to consider the other impacts that might come with a warming ocean and a warming atmosphere. And that is with El Nino generating, severe winter storms. They can definitely be much stronger storms, much more extreme storms. But this plot just kind of shows, this is overlaid the global surface temperature anomalies, and through December 2021, every one of those red bars are El Ninos, and then the blue bars are La Nina events. Okay. And some, just real quick here, what we typically see within our own area, this is climate area down here along the California South Coast. And typically what we see is we see more precipitation with El Nino versus neutral, and then La Nina, but that's not always the case, as we recently found out. 1997-98, very strong El Nino. You can see these very warm ocean temperatures as they were coming off the eastern equator. And look at what happened with precipitation, tremendous amounts of precipitation, 97-98. Meanwhile, strong El Nino of 2015-16. We gave just over 70 talks to communities and our government partners leading into the 2015-16 El Nino, between Eric Bolton, who's a morning coordination meteorologist in our office, Dave, I think you remember him, but we gave a lot of talks to get people prepared for a very wet winter. And we had to eat a little bit of humble pie, but we did say in those talks that El Ninos only tilt the odds to a wet winter in Southern California. All right. So there's no guarantee, but if you were to put a bet on it, you would bet on a wet winter. It didn't happen 2015-16. Moderate La Nina 98-99, very dry out here through Southern California. Really behaved as you would expect with a moderate La Nina. But then you go to the moderate La Nina of 2010-11, and look at how wet we were in 2000, the winter of 2010-11, all through Southern California. So very anomalous year. And then these are the current conditions that we're sitting at right now. A couple of things that stand out. For one, that black box, that's that Nino 3.4 area. Still in a La Nina condition. And then you look up in the North Pacific, we're still blobbing. There's the blob up there hanging on. And in fact, it's really had a strong impact on the jet stream. It's been really tough for us to get any sort of storms to really kind of ride where the jet stream can be far enough to the west to really pull into this moisture. And we get storms that what we call inside sliders that kind of dive down through California, and we end up on the wind side, like it's been lately around here. And then INSO outlook, we're expected to stay kind of in a La Nina regime through the summer. And there is a La Nina advisory in effect. And that website down there is where you can see where you can get more information on La Nina. So I'm going to speed things up just a little bit for the sake of time. This is a little bit on December versus January, February precipitation. December was crazy around here with the rain we had, over 300% of normal. We were lucky for what we got. And as a result, we ended up about normal. for this year, October to March. As you can see, those white colors through our 4-county area. Still warm, that you can see in terms of percentiles, either above to a bunch above normal. And our drought monitor, a little bit of improvement over last year from on the eastern side of the state, but not so much out here. So now the blob. The blob, it's a marine heat wave. And this was the real big one, May of 2015. And these are sea surface temperature anomalies. May of 2015 really stands out. It was brought about, it's not brought about by El Nino, okay? So those are separated. But when you combine that with the unusually weak coastal winds, it can affect the upwelling along much of the Pacific coast. And of course, that does have its effect on marine mammal life. And those weaker winds, we had strong high pressure. And as I said earlier, it's very difficult to get some of these storms that move out of the North Pacific and kind of are far enough west and south to really pull in any moisture. They end up being big wind producers and not much of a way in terms of precipitation. So this is I tested this link here before my talk tonight, and for some reason it's not working. It's a really cool site. I encourage you to check it out once in a while, see if it's back up again. But this is the California Current Marine Heatwave Tracker. And it's really kind of interesting when you look at that graph on the bottom and the total surface area of all heat waves, and the one from 15 and 16 really stands out. But again, even from 2012 all the way up until now, those green areas are 0 to 25%. So we're still kind of in that positive area there. And it's not going down. And the possibility, again, of having these kind of bump ups in heat wave, marine heat wave magnitudes it will always be there. So let's put it all together here. Some of the possible impacts on changing ocean marine mammals. And this is where I kind of go into, I dip my toes in the water here, figuratively speaking. And we talk a little bit about what these warm temperatures, climate change, El Nino, the blob, what impact they can have on marine mammal life. I invite you, based on your expertise and your experience and knowledge, to kind of help put things together too. But let's talk about upwelling first. And it's interesting that how important upwelling is, of course. It's not a secret, but as we get that deep upwelling with a very rich nutrient water, obviously that's a very important food source. And when you cut that off, that has dramatic impacts on ocean life, marine mammal life. But it's interesting, there has been some work that has been done where it's where you look at, this is an article here that was published in 2018. And what they did is they looked at coastal upwelling ecosystem with global warming and looking at the California current. Of course, that California current is a very important feature flowing down from the north. And when they model this, the California current over time, that will actually see the primary productivity have declined over the past few decades and continue to do so during ocean warming. However, global warming could enhance land sea surface temperature gradients, which in turn increase upwelling favorable winds. All right, so it's not necessarily all bad news. I mean, we need storms to really stir things up and bring that upwelling. But anyway, just kind of an interesting study that I ran across. So what are some of the things that lie ahead? We know these are the things that we know. The warmer water can trigger longer lasting and harmful algae blooms, warm water algae species, which is less nutritious for marine life. And that's the blob. El Nino events can reduce nutrient-rich upwelling, which impacts fish population, an important marine mammal food source. We know that goes way back in history again, fisheries off the South American coast and how they would be affected by El Nino. One of the most common responsive marine mammals to temperature changes is shifts in their spatial distributions. That's climate change. So as we're seeing warming oceans, we're seeing some of the certain species change their areas of where they're the habitat and their spatial distributions. Changes in water temperatures could alter the life cycles of the prey of marine mammals and provoke mismatches between the abundance of prey and those of marine mammals. So it's interesting because sharks are ectotherms. Dolphins are endotherms, and sharks don't need as much in terms of food, about 2% of the body weight, versus dolphins, about 12%. And again, I'm not a marine biologist by trade. I did stay at a Holiday Inn last night, but I thought that was very fascinating, in how you can get these mismatches between abundance of prey and marine mammals. So despite the large potential impacts of ocean warming on marine mammals, the global vulnerability of marine mammals to global warming is poorly understood. All right. And finally, could climate change bring about more upwelling along the California coast? That was the study that I cited in a couple of slides ago, that if we do have an increase in storms with very strong winds, that might actually increase that upwelling along the California coast. And then this is an interesting graph too, that I tried to spell it out here for everybody, but this was a study that was done back in 2010, where they looked at sea lion strandings, and looking at the causes of these strandings, from blue, which is out of habitat, which is, as you can see there, entrainment, hazardous location, harassment cases. The green is malnutrition. So again, especially when you see changes in upwelling and everything else. And then the yellow, fishery interactions, which is quite a tragedy when you think about that. But you also see some changes with that. And then what they did is they looked back at 30,000 stranding records in California, and to see if there was that connection with El Nino. Well, they peak in late spring, but only during El Nino conditions. But otherwise, they're constant throughout the year. So I highlighted, and this is broken down from the North Coast on the top all the way down to South Coast. And when you look in the South Coast, what I did is, in those red boxes, those are El Nino years. When you look at 83, 92, 98, 2003, and 2007. And those green bars, in terms of the strandings due to malnutrition, are really prominent in those years. And based on the kind of the birthing cycle and everything. And the fisheries interactions also increased proportionally. I would gather that many fishermen get pretty excited with El Nino and some of the catch that they can get. And so I think you've got quite a bit of activity out there during El Nino years. A lot of information on this graph. I'll just leave it up here for a second for everybody to kind of absorb. But this was out of the Ipcc special report. I've got the link there on the bottom, and it looks at the impacts from ocean warming, acidification, extreme storm events, and then other human impacts, and then the consequences from the coral reefs, polar seas, and fisheries. And quite a few negative impacts in there, of course, unfortunately, that you see, but a lot of information packed in here. I'll leave this slide up here for a second, and again, invite you to go check this out. There's a section there. It's an FAQ section, section 5.1, and again, this is the Ipcc. And then some useful links that you can go do your own research and play around a little bit. And I'll leave this up here for a while, but climate.gov it's an unbelievable one-stop climate shop. The climate dashboard that you see on the right there, that's available on that page. The Intergovernmental Panel on Climate Change. It's a starting point where that'll kind of launch you into tons and tons and tons of information. The reading is always very straightforward, great graphics, and a lot of information in there. The Fourth National Climate Assessment, there's a link to that. Check that out. That brings it down into more of a local backyard perspective. And in the National Climate Assessment, they do break it down into regions. So there's a section in there on Southwest region. And then the Climate Prediction Center's ENSO page, and this is where you can get all the latest on what's happening with El Nino Southern Oscillation. And finally, that bottom link down there, when it works, it wasn't working earlier today, but it's a really cool site, the Marine Heatwave Tracker. Hopefully the things will get resolved here and that'll be back up again. But anyway, really, really interesting page. So a lot of resources there to be able to jump off and get lots of information on climate change and ENSO and the blob. So that's all I have, and that's my contact information. There's our office there in Oxnard. If you would like to reach out to me by email or by phone. We're not in the office much today or right now. We're slowly reintegrating back. By the end of June is the plan to be reintegrated back to the office, but I do get voicemails sent to my email from my phone in the office. So Dave, I can stop sharing the screen, I guess, and we can go back and take some questions.
Yeah, that sounds great. Thank you so much, Mark. Lots to digest in all of that for sure. We had I had a couple questions. We had a question that was chatted in specifically about hurricanes, about what do we see as far as hurricanes and their relationship to climate change? What can you tell us about that?
Right. All right. So think about climate change and think about a warming atmosphere that can hold more water vapor. And so what we are seeing is not necessarily an increase in the number of hurricanes, but we're seeing stronger, more intense hurricanes. So we're seeing an increase in the, like the Cat 4, Cat 3s, Cat 4s, very, very strong hurricanes that, again, given all the other factors that's involved here, we're also seeing an increase in the amount of coastal flooding and tidal damage and things like that. The storm surge in a hurricane is actually one of the most deadliest parts of a hurricane. Everybody thinks winds, but really when it comes down to it, it's the storm surge that can cause the most damage. And considering all these factors, a stronger, more intense storm with stronger winds, more rainfall. I mean, there were the hurricane that hit the Houston area a few years ago. The precipitation amounts were unbelievable, unprecedented precipitation amounts of over 40 inches of rainfall with this hurricane, just incredible. So not necessarily more hurricanes, but more intense hurricanes.
Yeah, and storm surge is that kind of the wind speeds of the hurricane push water in front of it, building up this kind of ball of water in front of the hurricane that then kind of rushes on shore like a slow tidal wave coming in. And then rainfall on the far side of that. So all of the water trying to rush off the land into the sea, running into this water that's coming back at it. Both of those things together leads to all of that flooding and such damage. And then layer on top of that, when does it happen? Did it happen during high tide or low tide? And I think, if I remember correctly, Hurricane Sandy was unfortunately timed to hit New York at high tide. So that added to sort of the damage that occurred.
Yeah, it piles on.
It piles on. Really quickly, just you're a meteorologist. You said you're not a climatologist. What is the difference between a meteorologist and a climatologist?
Well, okay, meteorologist, it's interesting because when we look at my education and my training and everything, I'm really kind of looking at more of the here and now. If you want to really break it down, the national, we look out 7 days. Like we provide official forecast out to 7 days. One of the most important things we do is we provide information for our emergency partners and emergency sectors in kind of the here and now, like in that 3 to 5 day period. And really looking at again, when I had that very, very, very first bullet of storms make weather, weather makes climate. And a climatologist is looking at, the physics of the atmosphere is the same, but in terms of how the atmosphere interacts with the land over a longer period of time, much can be determined by what's happened already. Okay. But at the same time, you also have modelers that can now model climate and project changes to the climate over decades.
So maybe we ask the climatologist, what should we expect in the far future, and we ask the meteorologist, what should we expect in the next week as far as what we're going to get when we walk outside. Oh, I think we lost Mark there for a second. Hopefully he pops back in. Mark, you're back. Can you hear us? Oh. hold on.
Well, it wouldn't be right if you had one virtual call that dropped off for some strange reason.
Given we've had a global pandemic for like the last 2 years, I think this is the least of the challenges that we faced in the last.
I thought you had only paid for a 1-hour Zoom meeting, so that's why it cut off at an hour. Okay, I'm back. Sorry about that.
Okay, we had a question from Kimberly. You know, we've talked with words matter, right? And a lot of times we talk about climate change. Sometimes we talk about global warming. Can you kind of explain, is there a difference between global warming and climate change? Is it semantics?
It's a great question, because I personally prefer climate change, but climate change is a result of global warming. All right. And because of the warming atmosphere and all the domino effect of that, as I said earlier, can hold more water vapor. Now you get changes to that climate that aren't just related to temperatures. So climate change is a much larger picture, bigger perspective than the actual warming. Now, one of the problems when you say global warming, and I don't know how many times I hear it, but you know, you have these, it's minus 20 in Minneapolis and there's 3 feet of snow in Boston or whatever. Hey, what's going on with this global warming? Okay, well, that is weather, okay, and it's not the warming over a very long period of time, but we also are seeing an increase in, you know, in these winter storms like that as well. But again, I prefer to use climate change. There is warming, and that's kind of at the foundation of a lot of the Ipcc reports, as I had in that one first bullet of unequivocal warming. But it's what that warming brings with it.
Global warming is the mechanism. Climate change is the impact, maybe.
Exactly. Yeah.
Really quickly, just to clarify, sort of like we just described about hurricanes, El Niños, and well, ENSO. I believe you said that we don't necessarily see more El Niños, but we see more intense El Niños associated with global warming, climate change.
Well, no, that's right. So not an increase in the number of El Niños, but stronger. Now, since I've been here, we've had one real strong El Nino, which is that 2015-16. But you know, we've had, you know, going back before that as well. But when you look at the warming ocean, and as I showed that image that almost everywhere is warming, okay, when you look at it for a longer period of time, it's interesting to think that El Nino and La Nina are really all about that imbalance in temperatures and sea level heights between the Western and Eastern Pacific. And I think that kind of the takeaway is that with climate change, the effects of an El Nino are more intense, you know, because of, you know, we do have that warming ocean. We do have the overall sea level rise that goes with that. On top of that, the piling on factor, like we said earlier, and the fact that, you know, we've got our storms that are associated with these El Nino events, can be wetter, longer lasting storms as well. But from what I dug up, because I asked myself that question, are we seeing an increase in El Nino events? And the takeaway was that no, but then we could have stronger events.
All right, thank you. And it's that, I guess that's sort of the patterns that we're seeing, right? The types of weather events that we talk about, extreme weather associated with climate change, and you know, these types of events, when we get rainstorms, they're heavier rainstorms. If we get snowstorms, we get heavier snowstorms. We have droughts, they're bigger droughts.
Right.
You know, those kinds of things. The balance is extreme.
Well, and the important thing too, I don't know if it came out in my talk, but then we're seeing, you know, there's, you know, same thing. You've all heard of atmospheric rivers, probably on the news, and that's you know, the Pineapple Express is a variety of an atmospheric river. Well, there's been research on, are we going to see more atmospheric rivers with climate change? And the findings were that we wouldn't necessarily see more of them, but we will see a longer season and possibly for the ones that we do get, they'll be more intense. So it's interesting when you look at droughts, when you look at heat waves, when you look at extreme precipitation events. Not necessarily, they're very strong events, and it's a world of extremes. So like for us, exceptionally dry, exceptionally wet. We even saw it on a seasonal basis this year, 300% of normal precipitation in December, and then we end up almost having the driest January, February, March on record. So very big swings.
Yeah, I think it's especially important in California, given we're pretty water independent in California, and we rely upon a storage of Sierra snowpack as part of that. The slow release of the melting of snow from the Sierras is sort of what gradually releases waters into our system, which allows us to use that over the whole year. If we see more rain than snow, we're not seeing the same kind of storage of water. So even if we get a tremendous amount of precipitation in any one time, if it's coming down as rain, not snow, then our ability to use that water for the things that we use it for might be limited.
Would you rather see a big wad of cash, or would you rather have a big deposit into your savings account? I think
I'd like both.
Snowpack is the gift that I always say. Snowpack is the gift that keeps on giving, and we always should keep a close eye on the Sierra snowpack, especially the southern Sierra. Our three main, counting groundwater, our three main water sources are the southern Sierra and the California aqueduct. We also get water from the Colorado River basin. So really, we want to see a lot of snow up in the Sierra and then also within Colorado. And not to say that we don't want any rain down we don't need rain down here. But as far as a water source, definitely in those areas.
Yeah, we'll do another lecture on water in California. Maybe a series, right? That's more than an hour.
Right. Yeah.
All right. Any more questions from any of us out here?
I have a question, if you don't mind me talking instead of texting.
Yeah, jump in. Go for it.
I just want to clarify something back when we were talking about the difference between global warming and climate change, because like I said, when I introduced myself, I communicate a lot with the general public, and we're trying to get them to understand on their terms exactly what's going on. When they say, like you said before, a lot of people think global warming means everything in the whole world should be warm, from Texas to Minnesota to wherever. But that's not how it is, correct? It's just an overall, the temperature is rising compared to what it normally is. It's not like everything's supposed to be warm. Is that correct?
Well, that's correct. We still have a round Earth, and we still have uneven heating, and we're still going to have this constant battle of because of there's less heating in the poles than there is in the equator. You're having this constant battle of cold air, warm air, and cold air, warm air. And so you're always going to have winter storms, okay? And it's important when you think of global warming, you have to think of the time period that you're considering that. You have to consider it's an average over 50 years, for instance, and it's an average over the globe, for instance. But certainly you can have your areas within a certain season that is very cold.
Right. The other question I had to do with the strandings that you were talking about. You said that you noticed that during the actual El Nino, you find more strandings, but throughout the year, in general, it's constant. So we're still not sure if it affects the stranding?
Well, I think in that graphic that you saw, there was some definite peaks in those El Nino years, especially within the malnutrition cases. But in one of I don't have the slide in front of me now, but again, that was a statement that said they didn't see a big change throughout the year. So I think when you look at one year in particular, right, compared to other years, you'll see more of those, like fishery and primarily malnutrition when you consider the entire year. Or when you compare it against multiple years, you see that change, but there wasn't any. It was fairly constant across the whole year. So not really.
Not particularly during.
Not really like peaking at spring or, I think that the whole So there's pups, they're born in the spring, correct? Is that correct? Right.
They're born
so
it depends on what kind of pup you're talking about.
Okay.
Sea lions are born in June.
Okay.
And then northern elephant seals are born, I think, in like January, February.
Okay.
Yeah, usually up until March.
But they wean. They all wean sort of around the same time frame, around that spring time frame. So it's the most important part for malnutrition is looking at when those pups wean, when they go out to sea. And when we talk about strandings, we're typically talking about pups, those young of the year that come out.
Right.
And the availability of food for those novice animals that are coming out to sea, they're timed to come out to sea when it's supposed to be very abundant with life. The peak months for upwelling and when conditions are shifted, when there's not as much upwelling, adults might have a better ability to be able to withstand what's happening during the time. Pups maybe not so much.
How about that? Yeah.
Thank you.
Fascinating. Okay.
Thank you.
All right. Well, thank you so much, Mark, for joining us. It was fascinating, and I think what's really important is the data are right. The data tell us what's happening, and we see this really strong connection and understanding to what's going on on our planet in the direction it's headed. And we know that some of that change is baked in, that no matter what we do today, we're going to see changes into the near future. And our opportunity now is to mitigate the extent of those changes. So the efforts that we take today help us to make it so that we don't have to adapt to something so extreme in the near to far future. Even though we know we're going to have to adapt. So we as humans have technological capacity to be able to adapt and to move around, to use our technology. We think about animals, organisms, the environment. Do those animals have the same type of flexibility within their spaces? And for me personally, given that we have these really important breeding areas that are on islands that aren't going anywhere, off the coast of Oxnard, up by you, Mark. Conditions in and around those islands could be really important for the future of local pinnipeds. And what happens with upwelling, what happens with the extent and intensity of blobs and El Niños in the near future can be really important to the future of pinnipeds and marine mammals off the coast of California. So it's important that we have these understandings and that we keep a close eye on it. And places like Marine Mammal Care Center and the rest of the stranding networks and the work that we do in understanding ocean health as it relates to marine mammals is a really important additional data source that helps us with this understanding.
Well, I really appreciate you inviting me to talk to the group and sincerely appreciate all that you all do. There's always a soft spot in my heart for nature, of course, as a scientist. As a atmospheric scientist, but also the affinity to the ocean and everything. So I appreciate everything that you all do.
It takes a village.
Yes.
So thanks, Mark. Thanks, Kim. Thanks, everybody else. And we have a Sea Otter mini-series coming up for our next Beneath the Surface, starting on the 28th of this month, and then continuing on for the 5th. So keep an eye out on your Instagram, email, and whatnot for the next Beneath the Surface. We're going to learn all about sea otters. All right. Thanks, everybody, for joining us.
Thanks a lot.
And have a great weekend.
You bet. Thanks a lot. You too.
Bye, everybody.
Bye.